Tkalec from Slovenia. And looks like we're going to see some more interesting linking lines of some sort. So go ahead.
Okay, so good afternoon, everybody. Can you hear me? Is it great? So my name is Uroš Tkalec, and I will present a combination of experimental and theoretical work. So experiments have been done by me in the laboratory of Professor Mušević in Ljubljana, and accompanied theoretical results were also done in Ljubljana in the group of Professor Slobodan Žumar. So briefly, I will introduce the nematic liquid crystals and topological defects which appear in there. I will talk about nematic colloids. These are just mixture of spherical particles with nematic liquid crystal. I will discuss the mechanism of colloidal entanglement by defect lines. I will talk about also the topology of generated nematic braids, and we will see that you can make knots and links of disclination loops, and you can even classify them. And in the end, perhaps we can suggest also kind of a strategy for targeted design of a desired knot. So basically, these topics are described in these two papers recently published, and for more topological background on these topics, you can check also the very recent review by Kamian and co-workers. So, what are nematic liquid crystals? They are practically widely used in everyday life because we have them in LCD screens and in televisions, and they are actually liquids with orientational order. So they consist of rod-like molecules which tends to orient in the preferred direction, called the director. There are apolar molecules, and that's because of this director is a headless vector, and we have a line field. So we can describe the fluctuations from this direction by the scalar order parameter, or even more precisely to account both S and N with tensorial order parameter. Because these materials, of course, undergo also phase transition, we can model this by Landau-de Gennes expansion of free energy density, and because they interact usually with surfaces, you get also spatial variations of nematic order, which can be summed into three characteristic contributions: splay, twist, and bend. So, topological defects in liquid crystals are well studied since late 1960s, and they are defined as regions where the order parameter decreases actually to zero, and in these regions the order is actually ill-defined. And we can describe topologically the director field as a mapping from the medium to the real projective plane, which is in this case the ground state manifold. And we know two types of defects in liquid crystals. The first thing are disclination lines, which can be described by first homotopic, so the fundamental group, and this group should be Z2, distinguish just the defect and non-defect state. So, however, we can have different configurations of such defect lines. Here you can see that you can have plus 1/2 or minus 1/2 defects, which are topologically the same, but because of the energetic reasons and because of constraints induced by confinement, they do appear separately in different systems. Another kind of defects are point defects, which can be enclosed by a sphere, and then you can count the mapping order and thereby determine the topological charge. And these defects are enumerated by integers. So you can see here an example of radial point defect and example of hyperbolic point defect. And such defects actually appear very frequently in nematic colloids. So this is the field of research which started somehow in late 90s by the work of Poulain, where they observed that small water droplets inside liquid crystal do not coalesce, but they rather form ordered structures like one-dimensional chains. And our system is very similar to this thing. So we use colloids, several micrometer large spherical particles, which have a perpendicular orientation of liquid crystal molecules on the surface. And we enclose these particles in thin layer of liquid crystal. So the orientation at the surface is parallel. And because you cannot cover the entire space uniformly, you get a defect. So you can imagine that this sphere creates a radial defect, and to compensate its topological charge, another defect which looks like a black spot under the microscope has to be created next to the particle. Or if you confine this particle more severely, this point defect will spread into a loop encircling the particle. It's called the Saturn ring as well. So we will focus on such systems where we have particles encircled by defect loops. So what do we know about them? We know that such line defects are always closed loops with a constant cross-section, hyperbolic cross-section like here. And we have seen that we can make out of such loops nematic braids, so they can spread around many particles, and it's possible to rewire such defect lines by optical tweezers, or they can do this sometimes also spontaneously. So there is a question if we can do topological classification of such a restricted system and how it is different from what is already known. So first I will introduce the mechanism of colloidal entanglement. This is related to experiments which we have done several years ago, and where you have two spheres with encircled rings, and you locally hit the nematic region around them by applying the laser light. So you locally hit this, you destroy the order, the nematic order, and you turn off the laser light. So it is quenched down back to the nematic phase. So the order is again revealed, and what happens here, you see that out of two rings in the beginning, you can get a single disclination which entangles both particles. And we found there are three different, let's say, metastable configurations in the shape of figure of 8, figure of omega, or figure of theta. So they look quite similar, but the difference is at two sides. So if you look at these red regions encircled here, there is the difference between these configurations. And there was a very nice idea by my colleague Simon Chopar that you can enclose these defect line segments into a tetrahedron. So you can see that 4 vertices of tetrahedron can be connected by 2 defect strands in different ways. And you can switch then between these states by rotating the tetrahedron around the axis. So you can, if you just look at here and here, you see the difference in orientation of this tetrahedron. And you can do this many times, and you can come from these two disjoint Saturn rings to the figure of 8, figure of omega, or figure of theta. So to all these entangled states. And what is interesting is also that director field, which is everywhere normal to the faces, and it has a just hyperbolic cross-section at edges, it fits well also with the surrounding director field. So this is somehow the procedure how to change or how to rewire these structures among each other theoretically. And there is one more thing. So the disclination lines are not just simple lines, but they have internal structure. They have a threefold cross-section. So this hyperbolic cross-section. And they can be treated as ribbons, actually. And when they entangle many particles around, so they can acquire an angle offset of any integer multiple of this 120 degrees. And further, you can actually decompose such ribbons into two geometric parameters, so into twist and right separately. But there is another constraint in nematic colloids, which tells you that, so because the defect lines are confined to the sphere very tightly, the twist is not preferred in this system. So it's also because of elastic energy which is stored in the liquid crystal. It's very unusual to twist such a line. So we can say that twist is approximately 0 everywhere. And by saying this, you can tell that then right is this quantity which is quantized to third integer values. And because you know the Calogariano theorem, which states that the sum of twist and right is equal to the topological invariant self-linking number, you can then do something more. So you can introduce self-linking number which counts the embedded turns of the profile around the closed defect loop. Here are several examples how it looks like. And this quantization of self-linking number is actually directly connected also to the Barry's phase. So this somehow corresponds to the angular shift which is acquired upon the parallel transport of a surface binormal traveling along the surface of this three-sided strip. So you get this angle if you multiply 2 pi by the self-linking number. And then you can ask how these rewirings, so how these tetrahedral rotations are related to change of the right. And you can find this out by using the trantrix representation. So in this representation, you map, so you transform or you express the right in terms of surface area, which is on this unit sphere. And when you make the change, so when you change this angle, also the surface covered on the unit sphere will change. And using the Fuller formula, you can find out that by such rewirings, the right will change by plus minus 2/3. And you can generalize this principle to more loops. So you can then say that for a system which has many loops, you can compute the right as a sum of the self-linking number of individual loops and the linking number of a pairs of two loops. And finally, you can end up with a kind of conservation law which relates all these changes. So you see that tetrahedral rotation, which preserves the curve orientation, changes the number of loops by plus minus 1 and self-linking number by plus minus 2/3. And what is conserved here is topological charge here. So you can check for details in this paper, and the result is actually another interpretation of the result by Jenich 25 years ago. We will see the application of this law just a few slides later. So the complex topology was observed in liquid crystals already many years ago, especially by Yves Boligon. But he observed like Hopflings. He was studying also Mobius strips. There was also work by Turok, Jurke, and co-workers on defect coarsening dynamics. But all these structures were just transient and observed during the phase transition. So there was no manipulation tool how to stabilize these things and how to study them further. What we did is we used a system. Instead of homogeneous field, we made a twist. So that the molecular order twists by 90 degrees inside the cell, and you introduce the spheres here, and also the defect loop around the sphere will twist by some angle. So in principle, you get a crossing in Floris projection. And now what you can do is you can use the optical tweezers, so the optical trap, to bring together more particles and to entangle them in a similar way like before. So you can see that now these defect loops are spread around many particles. And what they can do, they can have different topologies. not only unknots like in these examples, but they can form also, for example, Hopf-link, or if you extend such arrays of colloidal particles, you can find also knots or links alternating if you add many rows here. And you can recognize by using the program of Rob-Sharain, for example, what these entanglements are. So what is the knot diagram finally. And maybe just to show some real experiments, how it looks like in reality. So you can do this by hand under the microscope. Here is one more example. So these defect lines behave as elastic stripes, you see. You can pull them, you can stretch them, and you apply enough heat to melt this order here, and then they reconnect with another strand. So, and by following such procedures, you can make many different topological structures, like figure of 8 knot or Whitehead link, or even some very big structures which are topologically very simple. That's not all. There is another thing. So you can also reconfigure the tangles. So if you concentrate on a region among 4 neighbors, you have 2 defect strands which can either cross or bypass each other in 2 directions, 2 orthogonal directions. And when you switch between these 3 tangles, so these encircled regions, you change the topology of entangled disclination entirely. So you can go from trefoil to some composite knot or to component link. So in principle, it's very simple like that, and it fits well also with these tetrahedral rotations which I was talking before. So another thing is the application of this conservation law, which we were mentioning before. So if you use it on such a system, you can see that if you plot a diagram of total self-linking number and the number of loops which you have, you can see that linked and unlinked structures alternate quite nicely. And you get kind of hierarchical organization of these structures in the diagram. But what is special, or what does not follow exactly this rule, is that you get knots on the outskirts of this diagram. So if you take larger grids, you would get many more around there. And this is the question, why it happens. And because tangles, so you can do permutation of tangles here in these spaces, are independent, practically every rewiring is allowed. And in principle, every knot is possible and link on a large enough colloidal array. And this, I think, is going to be proved also by Kemi and group soon. And maybe just to mention how do we know, what do we get, actually, is just the use of Professor Kaufmann's tangles, which are very naturally appearing in our system, and we then we then calculate the integer right and other parameters to get, of course, the Kaufmann polynomial first, and then we can recover the Jones polynomial and look up in the table what do we get. Just the last thing which I'd like to say is if we somehow ask the question, so if we want to do something, if we select, for example, Bormian rings, what do we have to do? First, we have to find appropriate array of the particles, then calculate, of course, the right configuration to find the right distribution of tangles, and we can realize this also experimentally. We did this for such 4x4 array, and you can see that we found close to 40 different knot and link types. So here are just prime knots and links are presented. There are many more composites as well. And you can see that in most cases you get quite simple structures, but you get also quite complicated ones with 9 or 10 crossings. So I think that this can be used as a kind of universal strategy how to obtain knots and links also in other systems, because it does not depend on material or on the system so much, but just on the organization of these tangles. So in the end, I would like to thank my co-workers, and of course I thank also to the organizers for inviting me to present these results here, and thank you, of course, also for your attention.
Time for one question.
Have you said that these structures are metastable or they are stable?
They are stable. So what was in this homogeneous field, which I was showing, just these dimers, colloidal dimers, they were metastable because the most stable state is just two separated loops.
Okay.
But when you are in the chiral space, so when you induce external twist, linked and these knotted structures are more stable than separate rings. So this was confirmed by numerical simulations. I was not showing this here, but so it is. I mean, the twist inverses stability of unlinked and linked structures.
So,
Okay. So thank the speaker.